Welcome back to our Chem 152 video series. In this video, we'll be talking about how to write acid and base reactions. Our first question gives us these two reactants, H2SO4 and H2O, and asks us to write the acid-base reaction and label the acid, the base, the conjugate acid, and the conjugate base. Our first reaction involves a strong acid. On the right side of the screen, you'll see that I've written the 7 strong acids that you'll need to know for Chem 152. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, and chloric. If you have any of those compounds, you are certainly looking at a strong acid. We see H2SO4 is on our list as sulfuric. This is how we know that we're dealing with a strong acid. We can begin by labeling H2SO4 as a strong acid. Therefore, whatever we react the strong acid with must be acting as a base. Let's think about what happens when we react these two together. In a Bronsted acid-base reaction, the acid will lose a hydrogen. And as it loses hydrogen, its charge will go more negative. Let's imagine what happens to H2SO4 if it loses a hydrogen. Currently it has 2 hydrogens. We can expect that it will go down to 1 hydrogen, and we write HSO4. Let's also check its charge. Right now, the acid on the left side has a charge of 0. If it goes more negative, it will go more negative by 1 step and drop to -1. Meaning that this HSO4 will also be -1 charge. You can symbolize that by writing a negative above that new compound. If we look at the base, the opposite will happen to that. Water is going to act as our base, and so we can expect it to gain a hydrogen rather than lose it and become more positive. That base has 2 hydrogens on the left side, so if it acts as a base, you add an additional hydrogen for a total of 3. Now we have H3O. Also, we're becoming more positive. On the left side, water begins with no charge, so we start with a charge of 0. If it becomes more positive, we're going to go more positive by 1 step and go up to +1. To symbolize that, we'll write a plus sign. Now that we know the products, let's talk about the conjugate acid and the conjugate base. In order to figure out which is which, we use this principle. What started out as the acid becomes the conjugate base. And what started out as the base becomes the conjugate acid. On the left side, as our acid, we had H2SO4. We can see in the course of this reaction it becomes HSO4, and that means that the HSO4 is in fact the conjugate base. On the left side, the base was water, and that becomes H3O, also known as hydronium. And so we consider the H3O+, since it came from the base, the conjugate acid. It's important to mention that the strong acids will always make H3O as a product. In fact, oftentimes in the literature, a generic strong acid is sometimes abbreviated as H3O or even just H+. So if you ever see H3O or H+ anytime in the literature, sometimes that will take the place of any strong acid. Those abbreviations are not oftentimes used in Chem 152, but if you take more chemistry, you may see them later. We can do a similar process with weak acids to figure out what the products are and what the conjugate acid and conjugate base are. Now, first we need to recognize that this compound, H2C2O4, is a weak acid. Now, in Chem 152, weak acids are anything that starts with H, or ends with COOH, or includes water, H2O, or ammonium ion, NH4 positive. So any compound that fits this description, but is not on the strong acid list, will be considered a weak acid instead. We can see that this first compound we start with is H2C2O4. We can consider this our weak acid, or it could act as a base. However, since we are definitely pairing up water with an acid, you can't combine an acid with an acid, and therefore water must act as the base. So since we have paired water up with something that's only an acid, we know that water cannot be acting as an acid here and must be acting as a base. Just like last time, to act as an acid, we will lose a hydrogen and go negative by one step. Since this compound begins with no charge, 0, it will go down a step to -1. And so we'll have HC2O4, 1 negative, and now we deal with water. Since water, it will be acting as a base this time, we will gain a hydrogen and go more positive by one step. Water begins as a neutral compound on the left, that's 0. It goes more positive to 1+. Therefore, we gain a hydrogen, we go from H2O to H3O, and put a positive sign on top. Just like before, the acid becomes the conjugate base, just as the base becomes the conjugate acid. So now we've seen two acids, a strong and a weak, reacting with water. Also note that with weak acids, when we show the yield symbol, we use a double arrow to show that it's possible for this reaction to proceed both forward and in reverse. For strong acids, we use a single arrow instead. Now let's look at cases with strong bases. You can recognize a strong base for the purposes of Chem 152 by being a group 1A metal connected to an OH or a group 2A metal connected to 2OH. There are many other strong bases out in the world, but this will basically cover your cases that you'll have to handle for this course. In order to make sense of the way strong bases work, we must show that the LiOH is a soluble compound, and when it dissolves, it splits into lithium plus and OH negative. The lithium plus is unreactive. Oftentimes in the textbooks, they will not even write the Li plus and just give you the OH minus instead. So what we need to think about is, what does the OH minus do with water? What we'll do is write that OH minus will be our base, which means that water must be our acid. Just as before, the base will gain a hydrogen and go more positive. So if OH minus gains a hydrogen, we now have two H's and one O. This actually just gives us back water. And if water acts as an acid and loses an H+, it goes from 2 hydrogens down to 1, and now it's just OH. We bear in mind that the base will go more positive from -1 up a step to 0. Therefore, this water has no charge. Our acid started as neutral, but when it loses that H+, it goes one step more negative. So you may be able to see that the reactants we started with on the left, OH negative and H2O, when you react a strong base with water, you get H2O and OH back again, and effectively, there's been no reaction at all. For this reason, you will not oftentimes show reactions of strong bases with water. We're effectively just assuming that the strong base will generate OH-. However, if we run through the same scenario with weak bases, we see something more interesting. If we have a weak base like Na2CO3, it may not be obvious that this is a weak base. We don't oftentimes notice that it could be a base unless we allow the Na2CO3 to dissolve. If we start with Na2CO3 and we break it into pieces, we will end up with 2 pieces of Na plus and 1 piece of CO3 2-, 2 sodium ions and 1 polyatomic ion, CO3, also known as carbonate. Now, sodium plus, just like before, because it's a 1A metal, it is unreactive. It will not take part in any further reaction. The interesting bit is the CO3 2-. Now, weak bases generally are either water or NH3 or anything that has a negative charge. Most things with negative charges are bases. However, there are some negatives that are not bases. I've written this as the super weak base list here on the right. If you see any of these, chloride, bromide, iodide, nitrate, perchlorate, or chlorate, all of these are not bases at all and are also unreactive. This means they will not take part in any further acid or base reactions. For the purposes of acid and base chemistry, you can safely ignore them. The wild card here is HSO4 negative. It acts as a weak acid and is able to give away its hydrogen as well. Be extra careful about that one, because if you see it, it's actually an acid and not a base, even though it is negative. However, other than what's on this list, most other negative compounds will act as bases. Therefore, to figure out what happens with this reaction, we're going to cross out the Na2CO3 and just write CO3 2-. Now, bearing in mind that our CO3 2- will act as a base because it is negative, let's think about what the water does. Because the CO3 2- must be a base, this means the water cannot act as a base and must be our acid. Now, the base will gain hydrogen and go up 1 in charge. This base starts at -2. If you go up by 1 step, you will become -1, and therefore our new compound is HCO3 1-, putting a negative sign to symbolize 1-. Since water is the acid, it will lose H and go down in charge. Since water started out as neutral, that's a charge of 0. If we go down by 1 step, we'll end up at -1, and therefore our other product will be O with 1H and a negative charge. That's OH-. Also, bearing in mind that this is a weak base, we're going to put a double arrow rather than a single arrow to show that this reaction could go backwards. Now, as with all the other reactions, the base becomes the conjugate acid, and the acid becomes the conjugate base. And so this is how we write a reaction of a weak base with water. Notice that this weak base has OH- as a product, just like a strong base does, but the difference is that the conjugate acid is now completely different from what you would get if you did this with a strong base. Thank you for watching. We'll see you again soon.